Hello.
There we go. Everybody have a good weekend?
Yes.
Good.
If you describe existential crisis as a weekend.
Yeah. All right, so I actually had a very busy weekend. I won't get into the details, but I did not have a chance to touch the mini exams that you turned in, so my plan is to have those graded tomorrow. So my apologies. And then your next one will be due, what, Wednesday?
Yeah.
Okay. All right, well, we are headed towards the end here. It's a good thing.
The end game.
We are talking about parametric surfaces and their areas. All right, so the first note here has to do with something we've done already, and that is from Chapter 10, Section 7, when we were talking about space curves and vector functions. Make this a little bit bigger. So we had said that if we define a vector function, r of t is equal to this vector f of t, g of t, or that's two-dimensional. In three-dimensional space, r of t is f of t, g of t, h of t. Then as we plug in different values of t, we will draw a curve in either two or three-dimensional space. So here was the first example from Chapter 10 that I gave with this. The vector function was r of t equals the vector t squared, comma 1 minus t cubed. And then if you just start plugging in values of t, you start drawing these red vectors, and if you draw them all, you're going to get some blue curve, right? And then in three-dimensional space, I gave you this example. This was cosine t, sine t, and then t over 5, and this drew us like a spring, right? Again, it is a curve in three-dimensional space this time, right? So now what we're going to look at is how can we draw surfaces with vector functions instead of curves. Now we can draw surfaces already. I mean, we've dealt with a lot of surfaces. One of the most basic examples of a surface that I guess we could look at right now would be something like that. That's a plane, right? That's the equation of a plane. We could do something like x squared plus y squared plus z squared equals 1. That's a sphere, right? So we know how to draw surfaces, but we want to draw them with a vector function instead of a scalar equation. Does that make sense? So can we draw things using this new concept where we have a vector function, but instead of plugging t into it, we plug in two variables, all right? So we have control of not just the t, but two things. We're going to call them u and v instead of t and something else. So let's say we are going to have a vector function, so it's going to spit out a vector. We're going to plug into it two real numbers, and it's going to spit out a three-dimensional vector. Now, each component of the vector that gets spit out is some function of the two things that we're plugging in. So this will be a function of two variables, this will be a function of two variables, and this will be a function of two variables. If we do that, then this will generate a surface in three-dimensional space. And I'll try and convince you why it does in a second. But these right here, these functions are called the parametric equations of the surface. So let's look at our first example. Well, yeah, okay. This is a definition, grid curves. Yeah, so let me try and explain this. If we have a vector function that takes in two things, right? Then if I hold one of these variables constant, Okay, if I don't, let's say I choose to hold the v constant, then we are back to 10.7 where we're just going to draw a curve, right? So if one of these is held constant, we're going to draw a curve in three-dimensional space. And the curve that we would draw is called a grid curve. So when we hold either one of these, if we hold one of them constant, we draw a grid curve, but that'll just be one curve on the surface. And I think this will come to light here in this first example. So there's your first example. We are defining a vector function r of u v to be equal to the vector sine u cosine v, sine u sine v, and cosine u. So do you all agree that this vector function has three separate parametric equations? The first one is the x one. Let's do sine u cosine v. The next one, the y is a function of two variables. It's sine u sine v. And then the last one, z, is a function of two variables, is just cosine u. And then I'm giving you some restrictions on the u and the v that we're plugging in. U is between 0 and pi, and v is between 0 and 2 pi. And I'm asking, do you recognize this at all? Do you recognize x being sine of u cosine v, y being sine of u sine v, and z being cosine of u?
Isn't that the sphere?
Yes, that's spherical coordinates, right? That's what we did when we wanted to go into spherical coordinates. We said, okay, our x is going to be, these are actually backwards. It was cosine theta sine phi, and then sine theta sine phi, and then cosine phi. So the u here is acting like the phi, and the v is acting like the theta. Does that make sense? So does this draw us a sphere? Well, let's see. Let's see if it does. So here's my geometric kind of illustration of what's going on here. I'm going to have to make this a little smaller, I think, so it'll fit. Okay, so the first thing I'm going to do is I'm going to start to draw some grid curves. So I'm going to hold one of the variables constant. In this case, let's hold v constant, all right? And let's let u change. So imagine v was constant, all right? So if v is constant, this right here is a constant. This right here is a constant, right? Agreed? Mm-hmm. And then what we have is your x and your y are going to spit out what? The same value, but your z is going to spit out a different value, cosine. But one of them is sine, the other one is cosine, and that should draw a circle, right? Sine, when you have sine and cosine like that. So if I'm holding v constant and I let u vary, just watch what happens to that dot. Okay, kind of hard to see what happens there. So what I'm going to do is kind of hold v constant and show you what happens as I change my u, right? It's going to draw that grid curve. And I'm fixing u to be between 0 and pi. Okay, so it draws me that piece of the sphere. Now what would happen if I just change v a little bit? If I change v a little bit here, then I'm going to have a different, I'll move it a little bit more, I'll have a different grid curve over here, right? Yes. Now I could have done it the other way. Let me bring v back. This time, let's hold u constant. If u is constant, then that stays, right? That stays, and that stays. And these are the two things that are changing, but again, they're sine and cosine. So I should be drawing circles again, but now it's going to be like this. So that's kind of hard to see again, so I'll hold u constant. Let me move them. Okay, right there. And let v change, and I draw that circle, right? Now, if I do all these different grid curves, then we start to create basically your standard longitude and latitude lines, basically on a sphere. Yes? Okay? So all of these together give us the shell of the sphere. Got it? So as you vary u and you vary v, you let them change, you draw the whole surface. All right, now, if you go back again to chapter 10, section 7, after we talked about vector curves or space curves, we talked about the derivatives of the space curves, right? We said, okay, well, what are the derivatives? Well, the derivative of a vector function, right, of one variable, gave us a vector that was tangent to our curve at a certain point. So the picture that goes with this was that if we had some vector function, so the blue, right, at every point on that blue curve, we have a tangent vector, which we can get by calculating r prime of t, right? Agree? So how is this going to work with these new vector functions of two variables? If we have two variables, then if we want to talk about a tangent vector, it's a little bit more complicated because it's a surface, right? So what we'll have to do is we'll have to hold one of the variables constant, look at that grid curve, and then get the tangent vector off that one grid curve. Does that make sense?
Wait.
So like this example right here. If I take back to that sphere example, if I hold v constant, then I'm moving along this green grid curve. So I should be able to go to some point on that grid curve and calculate a tangent vector off that green grid curve. Yes? But I have to hold v constant to do that. Yes? Now I could hold u constant instead and go around this grid curve, and then I would have a tangent vector for that one, right? So when it comes to these parametric surfaces, these vector functions of two variables, when we talk about derivatives, we're actually going to be looking at, or tangent vectors, there's actually two of them. One of them you get when you hold one of the variables constant, the other one you get when you hold the other variable constant, right? So it's going to give us two vectors. Make sense? Any questions?
And that's what would that just be your answer, just the two separate,
It depends on what they're asking for, okay? So I'm going to get to a question here. Let's make sure we understand the notation before. If we see that r vector function with subscript u, this means we're taking basically the partial derivative of r with respect to u. That means we're holding v constant. If we see that r with the subscript v, that means we're taking the partial of the parametric surface with respect to v, so we're holding u constant. So that's the notation we're going to use. All right? Now, can anyone just by looking at this picture tell me what the value of those two vectors, or what we could use those two vectors to now generate? A plane, right? So like whenever we had a space curve, right? A curve in three-dimensional space, we could find the vector that was the tangent vector, and then we could actually come up with a line, couldn't we? By just using that vector as our direction vector. Well, now we have two vectors, but if we somehow combine these two vectors, we should get a plane from those two vectors, shouldn't we? And that's the next kind of idea here, is that if we have these two partials, we should be able to get a plane. So tangent planes to a parametric surface. So if we're given a surface S, that surface S is drawn with this vector function. So basically this vector function draws that surface. Then we can always find the equation of the tangent plane at any point on the surface. So it's basically the same picture. There's my, there are my two vectors that I generate, right, off of those two grid curves. And then from that, we should be able to come up with the equation of that plane, shouldn't we? Make sense? All right, so let's do it. Let's do this example. Let's find the equation of the plane which is tangent to the unit sphere at this point. All right? Okay, so we want the equation of the plane, right? Equation of the plane. We know that the equation of a plane is a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. That's our kind of standard equation of a plane. Do we know any of this right now? No. We know the point, right? We have x naught, y naught, z naught. The only thing we need to know is ABC, but ABC is the normal vector. And how can we get that normal vector? crossing those two partial vectors, right? Those two vectors we get from taking the partials, cross them, and that should give us our normal vector. So we need to first we need to find out how we would draw this surface. How do we draw this surface S? Using what vector function? What parametric representation? What vector function of two variables can we use for the unit sphere? Yeah, the one we just did, right? Okay, so this was sine of u cosine v sine u sine v cosine u. And remember, the u is acting like the phi was, and the v is acting like the theta. So u is restricted here between 0 and pi, and v is restricted between 0 and 2 pi. So this right here is our vector function of two variables, and then this is our domain for that vector function. This is our domain. When you put these values into here and draw all the grid curves together, we get that surface S, which is the unit sphere, right? Okay, so now what we need to do is look at the partials, because the partial derivatives are going to give us those two vectors, right? So let's now take a look at what the partial of the R function is with respect to u. And that means we're holding v constant, and we're taking the derivative of this. So derivative of vector functions is real nice. You just do them one by one, right? Each component at a time. So what's the derivative of this with respect to u, treating v like a constant? Cosine u, cosine v. So cos u, cos v. And then the partial of the next part with respect to u, cos u, sine v. And the last one, negative sine u. Okay, so that means that if we're holding v constant and we go to any point on this surface, right? Well, I shouldn't say that. We hold v constant, it'll create a grid curve. This will give us the tangent vector on that grid curve. But you have to tell me what u and v are for me to tell you what the vector is. All right, next one, let's get the other vector, which would be the partial with respect to v. So now we hold u constant. So what do we get with this first one? Yeah, so this stays, right? Because it's constant, and take derivative of that, that's negative sine of v. So it'll be negative sine u sine v. And then the middle one, sine u cosine v. Oh, you know what? I just remembered something. What's the derivative of the last component function? 0. Okay, so I remember something last class. I don't know what made me think about it. Brenda, do you remember you asked me a question in class last time?
Like on Thursday?
Yeah, on Wednesday. You asked me a question about one of the, it was the problem where we were trying to show the work done was 2 pi for any curve that enclosed the origin. If you go back, if you want to watch that video, I made a notational mistake, and I think that's why you asked the question. We were trying to do an arbitrary curve. I called it C1, and then inside we drew a circle of radius A, and I called that C2. And then later on, when I was trying to find the parametric representation for this, we reversed the direction because we moved something to the other side of the equation, so it became negative. So I reversed the direction of that. And so what I did is this. I said, let's find the parametric representation for C2. And I said it was x was a cosine t, y was a sine t, and t was between 0 and 2 pi. And I think that's when you asked the question. I should have written here negative c. So everything I said was right, but I didn't put this notation down. And I think you asked me something like why is it backwards? It was after I finished the problem. So anyways, that notation, if you go back and look at the notes, should have been negative right there. I just put positive. So that would not be the correct representation because this is clockwise. Negative C2 is counterclockwise. So, okay, so I remember I was just thinking about that, and I was like, I'm going to go back and look at what I said, and that's what it was. So, okay, sorry, I just remembered that. Okay, all right, so This right here gives us our two tangent vectors on the grid curves respectively, right? So how are we going to get ABC from this? Cross these two, right?
Yes.
So the cross product of these two will give us the vector that is normal to our plane, right? Our normal vector. So let's cross these. So since I'm going to cross these, that's going to give me a vector, right? And to cross them, I'm just going to do them right up here. I cover this up, right? And I do this little thing. So I get 0 and then minus, but then that's going to become plus, right? So plus sine squared cosine v, comma. Now we cover up the middle one, and we do here to here at 0, and then this will be a minus again, but then I have to change the sign. So it's going to be plus, right? Plus sine squared u sine v. And then what about our last one? I'm going to run out of room here. What's that going to be? Cosine.
That's going to be cosine squared, sine u, cosine squared v.
Yeah, sine u, cosine u, cosine v squared. Yeah, I'm going to need more room than that. Sine u, sine v, cosine v squared, and then minus. So that was that, and then minus, but it's going to become a plus.
Yeah.
And then this time we have sine u.
V squared. Same thing, except it's going to be sine squared v instead.
Yeah, sine u cosine, isn't it sine u cosine u?
Yes.
Cosine u, and then sine squared v. You get it?
I think this sine v for the first one. There's no sine.
Let's see, hold on. This, we're talking about the first one?
Yeah, first.
This, I did them backwards, didn't I? No? This times this, so we get sine u, cosine, okay. Sine u, cosine u. Okay, that's that times that. And then this one be a plus, and then sine u, cosine u, sine squared. Okay, good, yes. And then what can we do with this? There's something nice about this.
They have a sine.
I can pull out a sine u, cosine u from both of these, and then what's left will become a 1.
Yeah.
So all of that really just becomes sine u, cosine u, right?
Yes.
Okay. Now, we're trying to find ABC, right? So how are we going to find ABC? This is the normal vector, right? But you have to tell me where we are. Like, where are we on the surface, right? We're at the point root 2 over 2, 0, root 2 over 2, right? That's where we are. So what you have to figure out now is what u and v take you to this point on the original surface function. So you're trying to figure out r of uv, how is that going to spit you out at root 2 over 2, 0, and root 2 over 2? So what is u and what is v that get you there? The reason why I need u and v is because I need to figure out what to plug in here for u and v to figure out what this vector is as a vector with numbers in it, right? So can you just tell by looking what u and v have to be?
U has to be power over 4.
U has to be pi over 4?
Yeah.
Okay, and what about v? So how'd you get u as pi over 4?
The last one is U.
So we have to match each of these up to their components, right? Like that, like that. So the easiest one to match is the last one, right? We can start there. I'm going to erase this. I know that cosine of u, must be root 2 over 2. And so that means that u must be pi over 4, right? I thought there was another place where cosine of u was root 2 over 2. Doesn't that happen over there at like 5 pi over 4?
Yes.
Yeah, but
But u is restricted here, right? U is between 0 and pi. So that's why there's only one answer here, right? All right, so we have that. Once I know that, what about the second equation? If I'm trying to make this one true, this is sine of u, sine of v must be 0, right? But you already know that u must be pi over 4. So sine of pi over 4 would be root 2 over 2. So this is really root 2 over 2 sine of v must be 0. And the only way that happens is if sine of v is 0, right? So this really turns out to mean sine of v must be 0. And where would that happen if v, remember v is between where? 0 and 2 pi. So the only place that the sine is 0 is where? 0 or pi, right? So we actually have two possible answers here. Do you all agree?
Yeah.
I mean, you could argue 3, 0 pi and 2 pi. Right? 0 pi, I should put v, must equal 0 pi or 2 pi. It could be any of those, right? Okay. But we have to satisfy the last equation. The last equation, I shouldn't have erased that. The last equation is that sine of u cosine of v must be root 2 over 2, right? We know for sure what u is. U is this, right? So sine of pi over 4 is root 2 over 2. Cosine of v must be root 2 over 2. So cosine of v must be 1, right? And where does that happen?
0 and 2 pi.
This only happens at 0 and 2 pi, right? 0 and 2 pi. So that eliminates that as being possible. So v here, this means that v must be 0 or 2 pi. And since 0 and 2 pi are correspond to the same point on the sphere, we're free to use either one. All right? That okay? Okay, so let's go figure out what the normal vector is. The normal vector for our plane, which was the partial of r with respect to u crossed with the partial of r with respect to v, would now be equal to, I should put here, at u is pi over 4, and let's go v is 0, okay? So at u is pi over 4 and v is 0, what would that cross product give me? And I erased it, so I'm just going to have to take all of your answers on faith here. What was the first component? It was like sine squared u cosine v. So what would that give us? Okay, I'll just put it here. You said it was sine squared u cosine v. What was the next piece? Sine squared u sine v. And the last one was just sine u. Was it sine u cosine u? Okay, so let's now plug in pi over 4 for u and v is 0. So sine of pi over 4 is root 2 over 2, and then square it. So you get a half.
Yeah.
And then times cosine of 0, which is 1. So you just get 1 half here. And then next one, sine squared of u again is going to be 1 half. But this time, what is sine of 0? 0. And then what about the last one? So root 2 over 2, and then root 2 over 2 again, right? So 1 half again?
Yeah.
So this is the vector that is basically sticking out at that point normal, right, to our surface. So the final vector equation, or sorry, not vector equation, the final equation of the plane that is tangent to this surface at that point should be a, b, c, right? So 1 half x minus x naught, which was root 2 over 2. And then plus b, which is 0, so nothing's going to be contributed there, right? And then finally plus c, and then z minus z naught, which is root 2 over 2, equals 0. So that should be the plane equation right there. Does that make sense?
Yes.
Start out with this. We came up with the vector function of two variables that drew the surface. We took the partials, we crossed them. Then we said, okay, how do we get to this point? We figured out the u and the v that took us to that point. We plugged that into the partials to get our actual normal vector, and then just plugged everything into the formula. All right, no questions? Keep going. Out of curiosity, if we have the unit circle, or unit sphere, I should say, not circle, and we go to the North Pole, what should the equation of the tangent plane be? Let's think about that plane that's up there. What's the normal vector going to be? What's the vector that would be sticking straight up? Like 0, 0, 1 would work, right? That would be a normal vector. That would be sticking straight up. And then what's that point? What's the actual point at the North Pole? So, I'm saying the unit sphere. So 0, 0, 1, right, would be the point. So the equation, right, blah, 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 equals 0, should just be 1, right? In front of the z part, z minus what's 1, right? So this should just, when we're all done, this is just z is 1, right? Which we probably could have said that from the very beginning, right? Because if you have a flat plane that's xy plane just moved up 1, it's z equals 1, right? Now, if you go back to our formula where we had the cross product, right? If you go back and you plug everything in, you should get this for our normal vector. You should get it. I'm just showing you, like, if you wanted to check that, you could show that it would spit this vector out. All right, let's see what the next note's about. Well, if we can find the tangent plane, then maybe we can find the surface area of this thing. Right? We can find this tangent plane. Agreed? We can find the equation of that tangent plane? So what if I wanted to find the total surface area of this surface? In this case, I'm using the sphere again because we've been using it. So we kind of have a little bit of a background with this shape. But in general, if I wanted to find the surface area of some surface, then what I could do is at each point, we could compute that plane, right? We could figure it out. More, we could figure out the area of this green shaded part, right? Because this vector comes from a partial, and this vector comes from the other partial, right? And how do you find the area of a plane spanned by two vectors? So if you have two vectors, you want to find the area. You remember what the area is? Not the dot. It's the magnitude of the cross product. So if you take the cross product of these two vectors, of course it gives you a normal vector, but the length of that vector is actually the area of this, which is crazy amazing, but that's the way it works. So that vector that comes out that's normal to both of those, how long it is corresponds to that area. So if you wanted to find the area of the whole surface, right, you would not just go to each point and calculate the area of this plane, right? It would be way too much, wouldn't it? Somehow what you need to do is scale this area back. So what I've done is I've come down here to this little red patch right here. And so what we're trying to do is imagine that this is like an infinitesimally small little patch on our surface. And we want to approximate it with something. Now this right here, we could use this as an approximation, right? But it would suck. It would be too much. So we need to scale it back. And when I scale it back, I'm scaling each vector, multiplying it by some constant that will shorten the vector. And I need to shorten it to where it's just kind of overlapping. But as you'll see, it is not perfect. Do y'all see that there's a little gap in there? You'll see that little gap between, I think you can kind of see it there. There's a little bit of a gap between the actual surface, the red, and then my little plane above it, right? But as you do take the limit and make that red thing get smaller and smaller, then that little thing above it basically becomes it. That error starts to decrease. And we've been doing this since the beginning of Cal 2. Cut it into smaller pieces, the error starts to go to 0. So the question becomes, what is the scaling factor that I need to multiply those vectors by to bring it back, right? We already know that the big rectangle, we can find the area by just taking the magnitude of the cross product of the partials. But what do we scale it by? Well, this, you're just going to have to take kind of on faith again. This right here is the area of that parallelogram, that rectangle. We are going to scale it by dA. Now, dA is an infinitesimal area that we get. Hold on. Let me go back to this picture. I didn't point this out in the first picture, but this right here was our U and our V. This is our domain. And so as I varied U and varied V, we drew all these different grids here, right? So if we want to take a little patch over here, right, and map it over here, it should map over to one of these patches, right? Yes? So a little square here will go over to this thing here. What we're doing is we're approximating this with the area of this thing, right, on top of it, but we're scaling it by this infinitesimal area right here. This right here is dA, the area of that little patch. So we scale it by this factor, and it'll bring it back to where it kind of covers like that. I'm not getting into the proof of that. I'm just saying that's what it is, all right? So this is our formula. This is our big formula for this surface area. Look, this formula allows you to find the surface area of anything. As long as you can draw it with a vector function, and you have some restriction on D, you can find the surface area of any surface. All right? The double integral over D of the magnitude of the cross product of two vectors with respect to area. So the surface area is the double integral over D of the magnitude of the cross product of the partial derivatives dA. So we can actually use that to find the area of the unit sphere. So somewhere on a formula sheet, there's a picture of this, and they give you the volume formula, 4/3 pi r cubed, and then they give you the area formula, and it's what? What is it? I think it's 4 pi r. No? Where's your formula sheets? I don't have them memorized. I have that one memorized. I don't have this one. Surface area of a sphere? 4 pi r? Is it r squared? Okay. Is that what someone said? No? Okay. So the surface area, okay, of a sphere is 4 pi r squared. So let's do this one. Do y'all want to do it for the unit sphere, or do y'all want to actually see if we can come up with this formula? I don't care. We can do either one. Yeah, let's come up with this. I want to give you the choice. Okay, so let's see if we can prove that the surface area of a sphere of radius r, okay, right? Radius r sphere has an area of 4 pi r squared. Let's prove it, all right? Okay, so here's what we're going to do. First, let's draw the sphere. So we're going to draw the sphere with the vector function. And the vector function is going to change a little bit. It's what we were just using, but we need to somehow incorporate the radius into it. So the only way it's going to change is that I'm going to have r, what did we do first? I think it was sine u cosine v, and then r sine u sine v. And then the last one will be r cosine u. Does everyone understand where the r is coming from? R is like the rho was in spherical coordinates. It hasn't been there before because it was a unit sphere. Now it's a sphere of radius r. Okay? Now from this, we need to calculate this. Do we have our restrictions on u and v? We have them, right? U goes from 0 to pi. V is like the theta, goes from 0 to 2 pi. That should draw us the whole sphere of radius r. We need to calculate now the partials. And once we calculate the partials, we need to cross them. And then we need to take the magnitude. Now, we already did a lot of this work, didn't we? We did the crossing earlier, but we didn't have the r's in there. So maybe you can look back in your work and you can tell me what those partials crossed together would have been had we had r's. That way I don't have to redo everything. So what would that cross product be? What would we have in there? Would it be r or r squared?
I think it would just be r because of the zero would cancel out the first one.
Maybe we need to go through this. Okay, let's do this. What is the partial of r with respect to u? Okay, let's go through this a little slower. What's the partial of this with respect to u? What do we have? Here, r cosine u cosine v, right? Next one, r cosine u sine v. And then the last one, negative r sine u, right? On the previous one, did I do u before v or did I do v before u? I did u before v, right? Yeah. Okay, so now let's take the partial of r with respect to v. Okay, with respect to v, we should get negative r sine u sine v. And then this piece here with respect to v should be r sine u cosine v. And then now that one should just be 0, right? Okay, now let's cross them. So now that you see it in front of you, what was missing? We were missing an r squared, aren't we? Yeah. On that first one, when we cover this up and we do this and this, right? We're going to get we're going to get an r squared on that one. And then when we go here to here, an r squared. So every one of our terms or factors was missing an r squared, wasn't it? Yeah. So just tell me what the old one was and I'll add the r squared to the front. The one we already did. It was sine squared u cosine v. The next one was now an r squared. What?
Sine squared u sine v.
Sine squared u sine v. And then the last one, we will still have an r squared. Sine u cosine u, right? We all good with that? Okay, now we need the magnitude of that, right? The magnitude of this. Now that we didn't have to do in the last problem. So if I take the magnitude of this, the magnitude of this will be, it's going to suck, but it is what it is. It's the square root of, maybe that's too big. This squared plus that squared, right? Okay, so what is this squared? R to the fourth, sine to the fourth u cosine squared v, plus r to the fourth, sine to the fourth u sine squared v, and then plus r to the fourth, sine squared u cosine squared u. Right? They all have an r to the fourth, so I can pull the r to the fourth out, and then I can pull it completely out of the root, and it'll become an r squared, right? Square root of Okay, sine to the fourth u cosine squared v plus sine to the fourth u sine squared v. I think you see what's going to happen. Sine squared u cosine squared u. So what happens on that first two terms right here? Yeah, we can pull it. Oh, I'm missing a u here, aren't I? I can pull out a sine squared u, or sine to the fourth u, right? If I pull out a sine to the fourth u, I'm left with cosine squared v plus sine squared v, which is 1. So this all together is just going to be sine to the fourth u, but then I'll still have over here plus sine squared u cosine squared u, right? Okay, now what?
You pull out a sine squared.
Pull out a sine squared u, right? If I pull out a sine squared u, pull a sine squared from each of those, right? And then pull that out as a sine u. What will be left under here?
Sine squared u
Sine squared u
plus cosine squared u.
plus cosine squared u, which will give you a 1, right? So at the end of the day, we have r squared sine u. Yes?
Isn't that rho squared sine phi?
That's basically rho squared sine phi
So it's the double integral
of 1 dA. But see, we don't have to go, we're not converting to spherical from Cartesian here. We are drawing a surface with two variables, and we are computing. It's going to turn out to be exactly the same as had we gone from Cartesian to spherical and we integrated 1. And there it is, rho squared sine phi. Okay, but let's finish it off. Okay, so now we want the double integral over d of the magnitude of partial r with respect to u across partial of r with respect to v, dA, which is now going to be the double integral. Let's go ahead and replace. We'll go 0 to pi, 0 to 2 pi. The order doesn't matter because these are both held between constants. This is now r squared sine u. And 0 to 2 pi was our restriction on v, wasn't it? Wasn't it on v? So I've got to go dv du. We're getting there. We're almost there. Seems a bit tedious, but nothing crazy, right? This is nothing too crazy, as long as you keep everything in order. Equals integral 0 to pi. Okay, antiderivative of r squared sine u with respect to v would be r squared sine u times v, right? Because r squared sine u is all a constant. So the antiderivative of that would just be that times v, evaluated from 0 to 2 pi. And then after we're done with that, du, sorry. So when we plug in, what do we get there? Integral 0 to pi. We're plugging in for v, right?
Yeah.
So we just get 2 pi r squared sine u. That's what we get when we plug in 2 pi for v. And then when we plug in 0 for v, it all goes away. Right? And then we have that du. Almost there. Antiderivative of that with respect to u would be negative 2 pi r squared cosine of u, evaluated 0 to pi. Right? So what happens when you plug in pi? Let's see. When you plug in pi for cosine for u, you get negative 1, and that creates 2 pi r squared. And then subtract from that. Now you plug in 0. When you plug in 0, you get cosine of 0 is 1. So now you get minus 2 pi r squared. And you put those together, you get 4 pi r squared. There it is. Okay? So we have proven that the surface area of a sphere of radius r is 4 pi r squared. All right, we have a special case, a special formula. And this formula can only be used when the surface you're looking at, okay, that R of UV, this can only be used when this parametric surface of two variables can be written in a way that its parametric equations look like this. In other words, your u, this part right here, this first function is just u, the second one is v, and then your last one, z, is some function of u and v. So it's kind of like u is just going to be u, so the x-coordinate is always just the x-coordinate, right? The y-coordinate is always the y-coordinate, and the z-coordinate is just some function of those two. When you have a vector function written in this form, then this is basically z equals f of xy. It is a surface floating above the xy plane, right, in three-dimensional space. It's a surface like this. But this only works when this is identically u, identically v, and then this is just some function of those two. Okay, so this special case handles the cases where the surfaces that we've dealt with in the past. If we can solve for z and get z to be a function of x and y, we can use this formula. What's great about this formula is that magnitude of the cross product, you don't have to go do it. You don't have to calculate it. All you have to do is this. And I put here y, and the way you could prove it is just go calculate this. And if you go calculate this with arbitrary values over here, you will always get this. Okay? Always. It'll look like this. So this becomes the new surface area integral. So I'm going to put over here, if z is some function of f of x and y, then that double integral now becomes the area, now becomes the double integral over d of the square root of 1 plus the partial of f with respect to x, that squared, plus the partial of f with respect to y, that squared dA. All this does is makes our life a lot easier and it's faster when we actually do a problem. I use some different notation here. Partial of f with respect to y. I just did f subscript y here. Same thing. Okay? So let's use this now in an actual example. Is it okay that I'm not going through this to show this? Is that all right with you? I mean, I don't mind showing it, but are you all okay? Okay. Okay. So here's an example. Find the surface area of the part of the paraboloid z equals y squared minus x squared, which lies between these two cylinders. So this is a paraboloid, and we want to know the surface area of that paraboloid that is between these two cylinders. So these two cylinders are vertical cylinders, right? One with the radius of 1, one with the radius of 3. We're looking between those two cylinders. There's some surface going between them. And we want to know the surface area of that. So this is the picture. We have two cylinders and then a paraboloid, which is kind of this orangish piece. We are trying to find the surface area of that thing right there. That's our paraboloid that has been restricted to the region between those two cylinders. Everyone get it? Okay, now we actually have done problems somewhat like this before, but we were trying to find like volumes. So we'd say like, hey, what's the volume of below this, right? Like below this down to the ground. What's the volume of that solid? That's not what we're asking for here. We're asking for the surface area of that surface. Understand? Okay, so can I use the special formula? Is the surface I'm trying to find the surface area of can be looked at as a function of x and y. Okay, which one is it? Z equals y squared minus x squared, right? So this is our surface, right? That's it right there. So I can look at this. I need to do the double integral over d of the square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared dA. Now in this case, f, I should have written this down, f is actually a function of two variables. It is y squared minus x squared, right? That is z equals some function of two variables. So let's go ahead and start filling out the integral. We need the partial of this with respect to x, which is negative 2x. Partial of this with respect to y, which is 2y. And now we can just plug in over here. So we've got double integral over d square root of 1 plus 4x squared plus 4x squared dA. 4y squared, thank you. All right, squaring each one. Now the critical point in this problem. We need to convert this double integral over d into like limits of integration, right? So d is the domain, which are your restrictions on x and y, right? Because x and y are the two variables here. So look at the domain of this thing. What is the domain in the xy plane? It's the circles, right? Those two circles. So when you look at d on the ground, here's x, here's y. When you're trying to figure out what d is, d was the stuff in between here and what was it, 9? Right, so 3. This is your domain on the ground, isn't it? So what do you think we should do? Go to cylindrical. Well, yes, we'll go to cylindrical. That's if we had a triple integral. If we're double, we just polar, which same thing, right? Okay, so this is a polar region, isn't it? So we've got to take this entire integral and convert it from Cartesian to polar. All right, so let's do it. Let's convert this from Cartesian to polar. Well, this region right here, x is going to become r cosine theta, y is going to become r sine theta. We all know this, yes? The restrictions on r and theta will now become r goes from 1 to 3 and theta goes 0 to 2 pi. So we're going to go to polar here, and then we rewrite the integral, right? So when we rewrite that integral, we will have double integral. Now we can put our limits of integration. Doesn't matter which order we go in, 1 to 3, 0 to 2 pi. If you want 0 to 2 pi on the outside, that's completely up to you. Then what goes on the inside? R, so we're going to have the r from the polar, right? So we'll put it in front, that's fine. R, that's from going to polar. And then we have that, right? Square root of 1 plus what? 4r squared. So we got lucky that we could factor out the 4. We have x squared plus y squared, which equals r squared, right, in polar. And then d theta dr. That's the way I chose to do it. I could go dr d theta, but I chose to go d theta dr. Right? Shouldn't be too bad.
Shouldn't be too bad, but still.
Is there a question, Danny? You're kind of, no?
Oh, no.
You're okay? Because when we do theta, there is no theta here, right? So we'll have a theta appear, and then we'll do 2 pi and at 0. So all it's going to do is throw a constant out front. So it won't be too bad. In fact, if you really wanted to do this,